And we are now recording. Now let's start first. I hate to do this because I'm going to do it every time someone else comes in. So will you remind me, once we get a fuller classroom, to go over all the stuff for the end of the term? Yeah. Okay. Because there's no reason telling you, and the next one comes in, and you tell him, and then the next one. So somewhere before people start leaving, remind me, and we'll go from there. All right. Any questions on anything we've done so far? Okay. We're in Chapter 10, which is conics, which we didn't do conic sections. That's 10.1. Parametric equations, that was 10.2 and 10.3. And then polar coordinates, that's 10.4. That's where we are now, good buddy. Okay. Okay. And this is sort of unusual to me that this little technology blob at the bottom of page 721, that they have this on the slide set. Sometimes they don't have all the exercises or examples on there, but now they'll put the technology. And I think we just started talking about this last time. Well, actually, okay. This figure here, 10.1, is the graph of r is equal to 1/2 theta. Okay? It was produced with a graphing utility in parametric mode. The equation was graphed using these parametric equations. X is equal to 1/2 theta cosine theta, and y is equal to 1/2 theta sine theta. Now, where do you reckon they got those? X is always r cosine theta, y is r sine theta. R was 1/2 theta, so they just plugged in the r. Okay? So this gives us exactly our x's and y's. And these are the values ranging from -4 pi to 4 pi. And as you see, and this is values for theta, and you see they get bigger and bigger and bigger as you go because you're multiplying something that's between 0 and 1 by something that's growing and growing and growing. So they stopped at 4 pi. And 4 pi, remember, that's about 12. But half of that would be about 6. And 1, 2, 3, 4, 5, 6, just a little beyond -6 there. 1, 2, 3, 4, 5, just beyond +6 there. So I'm guessing this is our -4 pi, and there's +4 pi. So they don't indicate the direction, but I can almost guarantee you it's going this way. From here to there, to there, to there, to there, to there, loops around, and then starts, going back out to there. Okay. The curve is of the form r is equal to a theta, and it's called a spiral of Archimedes. Now, how in the world did Archimedes come up with this? 200 BC. That's pretty incredible. He was an incredible mathematician. In fact, earlier in the text, we hit it in our Cal 1 this morning. He was mentioned as the greatest applied mathematician in antiquity. Incredible character. Okay? He's driving me nuts. And how in the world he came up with that way back then? That was way before Descartes. And he came up with the Cartesian coordinate system, but Archimedes had come up with this so much earlier. And just to give you an idea, every intersection here, because the cosine and sine, at -4 pi, of course, cosine would be 1, sine would be 0. Okay, so So that's why I figured we were out here, and if you started with a negative there, so that's why we started just past 3, no, I'm sorry, 6 pi, yeah, no, 6, half of 6 pi, 3 pi. Let me think again. Minus 4 pi, half of that would be minus 2 pi, and that would be about minus 6. That's what we're starting just past that. Okay, down here, when you go to negative 3.5 pi, cosine, of course, is going to 0 there. Sine is going to be negative there, so that's why we're down here. And here we're at 3.5 pi, that would be something less than 6, between 5 and 6. Okay, and then you go up here, and you should be at that was 2 pi, and this would be 5. So you just spiral literally inward, and then you start spiraling out. Good, we doubled the class size with Davis. Good deal. I'm not sure why they're focusing on this, except just telling you it's the spiral of Archimedes. So don't need to spend any more time on that. Interesting, the person, Archimedes, and other things too. Now, before we get to slope and tangent lines, though, there is example 4 that they do not show on the slide set. So let's do it here. Okay, example 4. And I've got to get my pen back. Okay, there we go. Now, and by the way, you can see larsoncalculus.com for an interactive version of this type of example. And by the way, I want to go over how the end of the term is going to be going, but with only 2 people here, every time someone else would come in, I'd have to say it again. So before anybody leaves, remind me, I need to go over that so I can have as many people here as possible. Okay? It says, sketch the graph of r is equal to 2 cosine 3 theta. So here's the graph, r is equal to 2 cosine 3 theta. And Justice is here. All right, top of the alphabet today so far, okay? All right. Now, when you're graphing on polar coordinates, the good thing to do, you need to include the whole graph. You usually don't go. Okay. First thing, and let's see, does it give us any limits here? None whatsoever. But I think we can look at it and see we're going to be within a circle of radius 2. Because cosine is never going to be outside plus or minus 1. So let's do a circle of radius 1 and a circle of radius 2, or approximately there. Pretty ugly. But this is how, rather than x, y, we're doing r theta. Okay. Now, what I would suggest, since theta is the looking like an independent variable, r is dependent, let's choose a theta. What's a good convenient theta to start with? 0. Always a good place to start. When theta is equal to 0, 3 theta, of course, is 0 also. What's cosine of 0? Cosine of 0 is 1. So 2 times 1 would be 2. So your r would be 2 when theta is 0. Theta 0 here, r2. See it? Theta 0, r2. All right. Now, pick me another good theta, and I like to go by the half pi's if I can get away with it. So let's do theta equal pi halves. What is cosine of 3 halves pi? Yes, 0, so the R is going to be 0. Well, we need something in between, okay? So let's go, and by the way, let me get Brandon, right?
Yes.
Okay. So let's pick something. How about, okay. Where I want to go with this is have cosine of pi halves. So that would be a theta being 2/3. 2/3 pi, right? So theta equals 2/3 pi. Now the trouble with that is that also gives us a 0. So we don't know how it got there. So let's pick something in between that. Let's say six. All right, here's Preston. Okay. The old gray cells aren't working well today. Okay. We want pi halves gets us to 0 also. So let's maybe do this thing to be pi thirds. So if this is pi thirds, then what we'll do is theta equal pi ninths. Does that work? Theta equal pi thirds, that would be pi ninths, okay? So theta equal pi ninths. What is cosine of pi thirds? Second? I think that's sine of pi thirds. 1/2, okay? And then 2 times 1/2 would be 1. So pi ninths is pretty small down here. I'm going to estimate it right about there. And there we're on circle 1. And then we get down to almost here. Now I think we can go to pi sixth. And that would be where we want to go. Pi 6 would be 30 degrees, and here we're at 0, right? Okay. And then let's do the same thing, continue and do we want this to be 2/3 pi, so let theta be 2/9 pi. No, that's not right, is it? Okay. Yeah. 6. Yeah, 2/9 pi. And what would that be? Theta is 2/9 pi. This would be 2/3 pi. What's cosine of 2/3 pi? Negative 1/2. Okay, so here's how you do this now. 2/9 pi would be an angle like this, and that would give you 1, but since it's going to be negative, you go down here, the opposite direction. So it's something about like that, I think. Okay. Then we do a, we want the argument here to be again, the old gray cells aren't working well. I think we want it to be pi. So theta equal pi thirds. Okay. Theta is equal to pi thirds. Then you have cosine of pi. And what's cosine of pi? -1. And 2 times -1 would be -2. So where do we start? Pi thirds. That would have been up here, but now we wind up down here. Okay? Now, the next one up, I'm pretty convinced is going to put us right about here. And then we'll be back at 0. And then, if I'm not mistaken, we'll be back around here. And then, I believe up here. And then down here, back at 0. And then over here somewhere. I'm sorry, I got this one wrong. This one comes up here, and then you come over here somewhere, and back to here, back to 0, back to here and here. And this is how it turns out. I can't draw these things well at all. Oops, wrong one. Back through 0 there. Supposed to be like a 3 propeller screw, okay? Approximately, okay? That's what it reminds me of. Probably not supposed to be that, but there's what we've got. Alternates. Maximum is at 2, comes into 0, going past that, then comes down here. Is that how? No. Here, 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 there. Yeah. So it faces that. Mine's pretty ugly, as you would expect, and that gives you your thing. Now, they actually say, and maybe theirs is a better idea, begin by writing the polar coordinates in parametric form, which if this is r, then your x is equal to r cosine theta, which would be 2 cosine 3 theta cosine theta, and y is equal to 2 cosine 3 theta sine theta. Now, to me, that doesn't help a lot, okay? It says, after some experimentation, you'll find the entire curve, which is called a rose curve, by letting theta vary from 0 to pi, and then, and they say you can use a graphing utility as well. Now, frankly, to me, this looks like a pain in the neck. I think, and the other wasn't a bed of roses, but you know, I think it's better just to figure out the convenient angles here, and for the argument here, and that would be 0, and I chose pi thirds because cosine of pi thirds was and is 1/2, and that makes for easy. So 0, pi thirds, and then I want this to be pi halves, so that would be, pi 6, and just keep going like that, so that you figure your angles, the easy ones to do, where this is 2, 1, 0, 1, 2, 0, and just keep tracking like that, and that will help you trace them out better. You've got to do the same thing here, and then you got to get the XY coordinates, and those are pretty awful themselves. So to me, it's actually easier to use R and theta once you get the procedure down. But take your time and be thorough with it. Get this argument here, so the cosine of whatever is going to make this one, make cosine 1/2. You know what it is. Back it up until you get there. then you want cosine. It starts with cosine equal 1, cosine equal 1/2, cosine equal 0, cosine equal minus 1/2, minus 1. Yeah, you pick the angle that makes it work for you, and then you know where to put it on the graph. And this is how I start the polar coordinate. Do my concentric circles to be at least as large as the largest circle needs to be. Okay. This way, I guess will work too. That looks even worse. I mean, frankly, that looks way worse. Okay. Now, it says use a graphing utility to experiment with other Rose curves. Note that the Rose curves are of the form R is equal to A cosine n theta. Okay. Now, it's a little early to generalize, but the A appears to be the maximum diameter, or radius. Yeah, radius. And this produces 3 petals. So maybe a 4 for N would produce 4 petals, and a 5 for N would do 5 petals, and that's what they are suggesting here. No, sorry, not quite true. The 5 N equal 5 does produce 5 petals, but N equal 2 produces your 4 petals. The thing is, they're thicker petals then. So the even petals go different from the odd petals. But that's just sort of a fun thing to play around with to see what you get. Okay? But for sure, the whatever the A is, that's going to be your maximum radius. Okay. Now I think we're ready for slope and tangent lines. All right. To find the slope of a tangent line to a polar graph, consider the differential function to be a differentiable function to be R is equal to alpha theta. Okay? To find the slope in polar form, use parametric equations. X equal R cosine theta, which is alpha theta cosine theta, and Y is equal to R sine theta, which is alpha theta sine theta. Now this is sort of, to me, a little bizarre way of doing it, but it's fine. It's certainly true. And then what we want to do ultimately is have dy dx, right? That's your slope. Okay? That's what we're looking for, slope and tangent lines. Well, to get dy dx, do dy d theta, dx d theta, and then dy d theta divided by dx d theta is going to be dy dx. So that's the route we're going to go. But of course you have that unknown function, alpha theta. So let's see what we do. Yeah, they're changing it to t's now. Why? They started with theta, which is fine with me, but they're going to t's here. So here is theorem 10.7. Seems like to me they've got things a little backwards here. They do this in the book first and then do this. Here they do it reverse order, but it's okay. If smooth curve C is given by these equations, y, x equals alpha t, y is equal to g of t, and the slope, and this isn't quite the same as what we had before, so I think I see why they went to t. The slope of C is dy dx, which is dy dt over dx dt, as long as dx dt is not equal to 0. So using the parametric form given here, backing it up to our thetas, that would be, and this to me is, we should have done first, dy d theta would be, let's go back and do it where it belongs, okay? So let's go on and do dy d theta here. You tell me. Forget this one, go right there. What would that be? Second? Second? I can't. It'd be alpha theta cosine theta. We don't know what alpha theta is, but alpha theta cosine theta, that's the first part. Anyone know what we're doing? Product rule, right? And how does that go? We did first times derivative of the second, plus second, which is sine theta times derivative of the first. So I'll put F prime theta sine theta. Similarly over here, let's do dx d theta. Okay, again using this form. And what do we have there? Negative alpha theta sine theta plus F prime of theta cosine theta. Okay? Now, our dy d theta is going to be the quotient of those two as long as dx d theta is not equal to 0. Okay? And unless the elfs are sort of funky there, I think most of the time it won't be. I say most of the time. There will be times it won't be. Because sine and cosine are never 0 at the same thetas. So those two can't make it 0. It's going to have to be the f's and f primes. So the dy dx is going to be the quotient of those two. Alpha theta cosine theta plus f prime theta sine theta divided by, and I like to rearrange the order. I don't know if this is fair to do or not. I mean, it's fine. Cosine theta minus f of theta sine theta. I just don't like leading off with a minus sign, so that's why I changed that. So let's see if that's what they get over here. Yeah, that is. They kept it in the other form. And that establishes the next theorem. Okay? Slope in polar form. If f is a differentiable function of theta, then the slope of the tangent line to the graph of r is equal to f of theta at the point r theta is given by that, exactly what we just determined, provided that the dx d theta is not equal to 0 at r theta. Okay? So, throughout a graph here that they don't give us much about, I guess it's just a generic graph. Okay. So see the figure, there it is. And there's nothing on this graph that makes me think, oh, I see why that's the thing. It's not there for me. But that's what the tangent line looks like. And it's going to depend on how x changes with theta and y changes with theta. Okay. Now, of course, you will see the places that will give you problems. Where you have a vertical tangent line here, that would be where the dx of theta is going to 0. Also, that would be a defined tangent line for that. I don't think there would be any problem up here. That would be where the y of theta is equal to 0, which is fine. No problem there. So, okay. From that theorem, this one right here, okay, you can make the following observation. I think I just did. Solutions of dy d theta equals 0 yield to horizontal tangent lines, provided that dx d theta isn't 0 at the same place. Then you got the big problems on your hand. You can't determine much of anything. But solutions where the x d theta is equal to 0 yield vertical tangents, provided that dy d theta is not equal to 0. Okay? And if dy d theta and dx d theta are simultaneously 0, no conclusion can be drawn about tangent lines whatsoever. That's an indeterminate form, which we don't mess with. We used to sort of like having those because then we could see if there was a limit. Right now, we don't like them very much. Hey, William is here. All right, good deal. I think we may still be having some more people come in. I'll wait a while. I haven't made any announcements or things about that. I want to get more people here so I don't have to repeat them every time someone else comes in. So before anyone has to go, remind me to go over how we're going to end up the term. Okay? All right. So we're doing, in Chapter 10, we didn't do conics, so we did parametric equations, and now we're doing polar coordinates. And we're in 10.4, which is polar coordinates and polar graphs, and we just are at the top of page 723, if that's helpful to you. So I think we're ready for example 5. Find the horizontal and vertical tangent lines of r is equal to sine theta, where theta is between 0 and pi. Theta can be 0, but can't be pi. Okay? So how are we going to get the horizontal tangent? Second? Okay, the horizontal tangent is where dy d theta is equal to 0. But, wait a minute here. What is your y? Okay. Y is always r. Help me, somebody. What's the parametric equation for y? The conversion equation, you might say. Say again?
Is it r squared?
Not yet. We're going to be at r squared in a minute. Y is equal to r, no, sine theta. I'm used to doing x first, but since we're doing y first, y is always r sine theta. Think about this, okay? If you got an angle here, theta, then, and this is your radius, the x value is r cosine theta, the y value is r sine theta. Always, okay? So this is, doesn't look like an N, does it? Okay. All right. So your y would then be r sine squared theta, right? Because y is r sine theta, but r is sine theta, so this is r sine squared theta. Now we can do dy d theta, okay? Except, let's plug back in, y is equal to, and this is sort of redundant, I'm going in circles here, I is equal to sine theta times sine squared theta, right? Which is sine cubed theta. I think. Okay. Now do dy d theta. This doesn't seem to be going well, does it? That's not right. Wait. Yeah. Okay. Let's back off. In fact, let's erase it all and start over. Find the horizontal and vertical tangent lines for this. So like you said, this is where dy d theta is equal to 0. No, dy dx is equal to 0. Okay. Which will be, of course, where dy d theta is equal to 0. Okay. And since y is equal to r sine theta always, then y is equal to sine squared theta. How in the world I got off onto the other thing, I don't know. R is sine theta times sine theta is r sine squared theta. This is what we do dy d theta. What would that be? Say again? 2 sine theta times cosine theta. Exactly. Chain rule. Power rule, then chain rule. Okay? And where is that equal to 0? 2 places. Okay? Certainly 2 is never equal to 0, but where is sine theta equal to 0? Between 0 and pi. Where is sine theta equals 0? Between 0 and pi. Second? 0. So theta equals 0. It would have been at pi also, except pi is not included. Okay? But it's also 0 where cosine theta is equal to 0. And where between 0 and pi is cosine theta equals 0. So theta equal pi halves. All right. So 2 places there where the first derivative will be 0, we think, at least potentially. Okay? So that's the horizontal tangent lines. Okay? Let's see about vertical. What's true about vertical tangent lines? Yeah, dx d theta equals 0. Okay? And where is that going to be true? Well, let's see. X is equal to r cosine theta. And if r is sine theta, this is sine theta cosine theta. Okay? So then what is, this is your x. What is dx d theta? Product rule. And what does that give you? A little louder. Cosine squared theta, because its derivative of sine is cosine times cosine is cosine squared, minus sine squared theta. Okay. Now does that sort of ring a bell somehow? What is that? No, it's not 1. Plus would be a 1. This is a minus. No bells going off, huh? Okay. How about this one? What is cosine alpha cosine beta minus sine alpha alpha sine beta? Does that ring any bells? I'm guessing not. Any? From anybody? How about this one? Well, I don't know if I can do it anymore. That is cosine 2 alpha. Okay. This cosine alpha plus beta is what that one is. Okay. Okay. That doesn't ring a bell, huh? If you go back now, I keep forgetting in this book where it is. I believe this is in trigonometry, which is front of your book. That front page, that's sort of a cardstock page, the back side of it, the double angle formula is what I'm getting at. Cosine of 2u is cosine squared u minus sine squared u. That's where I was wanting to go with this. So this is dx d theta is that. But is that any better form to use than the one I was? I don't think so. Let me see. I think we can use, let's see about just using this one. Nah, let's do it this way. That's equal to cosine 2 theta. Cosine squared minus sine squared is cosine 2 theta. Okay? And where is that equal to 0? Between 0 and pi. Where is cosine equal to 0? Pi fourths, is that what you said? Okay. Yeah, that would certainly, yeah. Where 2 theta is pi halves, yeah. So theta equal pi fourths. That would certainly give you a cosine equals 0. Any others? Where else is say again, 3 pi fourths, is that what you said? Yes. And theta equal 3 pi fourths. So those are the two values there. One value for sine, well, no, one, so 4 values total. Okay. These two are when you have horizontal tangent. Okay, and these two are where you have vertical tangents. The reason we couldn't be specific at first, we wanted to make sure that there was no place where both of them were 0. And there wasn't. That's why we held off saying these are horizontal tangents to begin with, because we wanted to make sure that when we did the vertical tangent, the cosine, the dx d theta equals 0, that none of these were the same angle here. If that was the case, no, you can't tell. But since they're two completely different ones, yes. 2 horizontal tangents, 2 vertical tangents. Does that make sense? Okay? Uh-oh. Okay, I think we're all right. Except that found the horizontal and vertical tangent lines. Oh, tangent lines. They didn't say the positions for the tangent. They said the tangent lines. So what we need are the points is basically what we need. So we know that when theta is equal to 0, that's where a horizontal tangent line is, right? Well, that would be, r would then be 0 there, so our point would be 0, 0, okay? And this one at pi halves, that would be r is equal to 1, so that would be pi halves, I'm sorry, 1 pi halves, it's r theta. Okay. 1 pi halves. Those are where the points where you have horizontal tangents. The points where you have vertical tangents, that would be at theta equal pi fourths, and sine of pi fourths is what? Square root of 2 over 2. So those points would be root 2 over 2 pi fourths. It's a horizontal tangent. And this one would be, and when theta is 3/4 pi, what sine? it's still square root of 2 over 2 minus pi fourths. All right. Now, if you want the equation for the tangent line, they're really easy in the xy values. X equals 0, that's going to be the horizontal tangent line. No, I'm sorry, y is equal to 0, horizontal tangent line, and y is equal to 1, that will be your vertical tangent line. Okay? Your horizontal tangent lines would be x equal to 2 over 2. No. Should be a negative. Why have I not got a negative there? No, yeah. X equal negative root 2 over 2, that would be this one. And x equal positive root 2 over 2 would be that. Now those are the horizontal and vertical tangent lines in x's and y. Really easy to write that way. If you're writing them in r theta, are they even writing them in r theta? No, I don't guess they do. They just draw them. So that's all they said. Find the horizontal and vertical tangent lines. I guess what we didn't do is do our graph. And since I'm not particularly hankering to graph it, let's just let them graph it for us. Okay? All right. This is Corbin. Anyone else come in since I called roll? Okay. So let's let them draw it for us. Begin by writing the equation in parametric form. X is equal to sine theta cosine theta, exactly what we did, and y is equal to sine squared theta, exactly like we did, only I started with y. Okay? Next, differentiate x and y with respect to theta, and set each derivative equal to 0, and that's what we did too. dx d theta is cosine squared minus sine squared, which is cosine 2 theta, that's 0 at pi fourths and 3/4 pi. And dy d0 to sine theta cosine theta, which happens to be sine of 2 theta, which we didn't do because we could set each of those equal to 0 individually, and that's true where theta is equal to 0 or pi halves. It would have been at pi, but that's not in your domain, just outside. So the graph of the tangent line, and they didn't even say, here is the function. What was it? R is equal to sine theta. Okay, so theta is equal to 0, R is equal to 0. And theta is equal to pi fourths, sine of pi fourths is 2 over 2. It's equal to 1, with the sine of pi halves is equal to 1. Equal to minus 1, not minus 1 half, that's where I'm not buying this. When theta is 2 over 2, well, theta is 3/4 pi, we know that that is root 2 over 2. What is it about this that makes that a perfect circle? Sort of looks like it is, and everything indicates it is. Should we have been able to tell that from the beginning? I'm not absolutely certain we could. Now, I think what you were suggesting before, when we had r is equal to sine theta, okay, if we were to square that, you'd have sine squared theta. And I'm not sure that's going to be helpful.
I was just thinking it would be the diameter.
What's that?
R squared would be the diameter.
Yeah, no, the radius.
Yeah.
No, r squared is the square of the radius. So it's not 2r. 2r would be the diameter. Okay. Okay. Try it this way. R is equal to sine theta. That was our original, right? Let's multiply both sides by r. So this is now your y value. Y is equal to r squared. Okay? And r squared is x squared plus y squared. Okay? So that means, that may be it. X squared plus y squared minus y is equal to 0. And this would be x squared plus, if you complete the square here, half of this would be plus 1/4, and add a 1/4 here. Second. No, you square it once you take. Yeah, only, and that's a plus, and you add it there. So this would be a y minus 1/2 squared. Okay, multiply both sides by 4, and you have 4x squared plus y, 4 times y minus 1/2 squared is equal to 1. Yeah, that's and that's the same as x squared over 1/4 plus y minus 1/2 squared over 1/4 is equal to 1, and this would be 1/2 squared. This would be 1/2 squared. So yeah, you have radius of 1/2. If you multiply both sides by 1/2 squared, then you have x squared. Yeah, that might be a piece of squared. Do it. X squared plus y minus 1/2 squared is equal to 1/2 squared. Okay, so radius is 1/2. Sure enough, that's the case. Radius is 1/2 in every direction. Your x, the center here is at 0, and the y value in the center is at 1/2. So yeah, it's a circle centered at 0, 1/2, radius 1/2. That is exactly the case. Okay, rather bizarre but true. They didn't do that for you, but that's how you could do it if you wanted to. And let's see, do they do example 6? Yes, they do. Find the horizontal and vertical tangent lines to the graph of r is equal to 2 times 1 minus cosine theta, where theta is between 0 and 2 pi. Not counting 2 pi, but counting 0. Okay. Now, what we need first is trying to find some way to get this in terms of our x's and y's. So So since R is equal to, say it the other way, X is equal to what? You tell me in terms of R and theta. R cosine theta. Okay? So that would be X is equal to 2 cosine theta minus 2 cosine squared theta. Right? Just multiply cosine theta times this thing. I believe that's right. Everybody agree or not? Okay. And y is equal to, help me, r sine theta, and that would be equal to 2 sine theta minus 2 sine theta cosine theta. Okay? What we want to know for horizontal tangent lines. dy d theta to be equal to 0. And what is dy d theta then? Two cosine theta minus put a 2 cosine squared theta minus 2 but a plus then, right? Sine squared theta. Everybody agree with that or not? Okay. Now, and we want where that's equal to 0. I think I'd prefer to have everything in one trig function, wouldn't you? So how could we get either one of those into the other? What would be the easiest way? Say again?
2 cosine theta minus 2.
Okay. 2 cosine theta minus 2. Okay, that's factoring out a cosine theta. Is that, no?
The cosine theta is squared
Okay.
plus sine squared.
Right. Sine squared is 1 minus cosine squared theta, right? Isn't that what sine squared is? Sine squared plus cosine squared is 1. So let's plug that in and we get 2 cosine theta minus 2 cosine squared theta, and then we got plus 2 minus 2 cosine squared theta, which I think comes out being, let's just factor out a 2, okay? And that would be still 2, I'm going to make it minus 2 cosine squared theta plus cosine theta plus 2, plus 1. All right. Now what I'm going to do is factor out a minus 2. I don't like leading off, so yuck. Okay. Let's do it. Minus 2 times cosine squared theta, or 2 cosine squared theta, plus cosine theta plus 1. Now, yeah, you're right. Those are minuses, aren't they? Is that what you're saying? Yeah. Okay, you're absolutely right. Okay. That's what I meant to do, but I got carried away. Okay. Now, first question, can we factor that? Anyone have a hint on whether we could?
Yes.
I think we can. 2 cosine theta times a cosine theta, and then there's going to be a plus or minus 1 and 1, and I think if you make this the minus and that the plus, that should do it for us, shouldn't it? Is that right? Got it? Did I do it right? Believe so. Okay. Everybody in agreement? Okay, and where that's equal to 0, obviously negative 2 is never 0. So that's not going to contribute anything. So it's 0 where 2 cosine theta plus 1 is equal to 0. Can you tell me right off the top, or do I need to do a little manipulation? Subtract 1 from both sides, and you have 2 cosine theta equal negative 1. Divide by 2, and you have cosine theta is equal to negative 1/2. Where's that true? Where is cosine theta equal to negative 1/2 between 0 and 2 pi? 2 2/3 pi, exactly. So that's true at theta equal to 2/3 pi. Okay? How about cosine theta equal 1? Because that would be the second part here, where cosine theta minus 1 is 0. That would be where cosine theta equal 1. And where is that true? Second? Yeah, exactly at 0. Would have been at 2 pi again, but it's not. So theta equal 0. So 2 horizontal tangent lines, we think so far, at these 2 values. All right, now let's do the vertical tangent line. That's where dx d theta equals 0. And someone tell me what that will be. Dx d theta equals, let's just do dx d theta first. It's an ugly x. Let's see if I can clean it up a little bit. Not much better, but a little bit. What's dx d theta? Help me. Help me. Negative 2 sine theta, is that right? Okay. Next. Cosine theta. Okay, so I'll make it plus sine theta. Okay. Now, that one's not quite, well, not bad. Still not bad. You don't need to get them all in terms of sine or cosine, because you can factor out the sine, right? In fact, let's factor out a minus, well, let's factor out a 2 sine theta, right? And what do you have left? Negative 1 cosine theta. And that's supposedly equal to 0, right? Well, 2 is never equal to 0, so we don't have to worry about that. Whereas sine theta equals 0. Second? No, sine theta. 0, so either theta equals 0 or one other place between pi. Okay. Now, Houston, we have a problem. We have a theta equals 0 here and a theta equals 0 here. We can't have them both. Okay? So that place is not determined. Okay? How do they express that? If they're simultaneous, then no conclusion can be drawn about the tangent lines at 0, 0. We just don't know yet. We may have to draw a picture or something like that, but that is an issue. Okay? But, where was our second one? Theta equal pi, no problem here. Okay? So that's all right. All right, the second place is where 1 minus 2 cosine theta equals 0. In other words, that's where cosine theta is equal to 1/2. Okay, and what's true about that? Where is cosine theta equal 1/2? Pi over 6. Is that what you said? Equal pi 6. No. Pi thirds, isn't it? Oh, okay. Say again? Okay. It's pi thirds. Okay. I couldn't hear what you said, but I can't get the pen to write. Pi thirds. Now, is that a problem? No, 2/3 pi would have been, but that one's not. Okay, so it looks like we do have a horizontal tangent when theta is equal to 2/3 pi. Okay, and we have a vertical tangent when theta is equal to 1/3 pi. So this is vertical, this is horizontal. Okay, now seems like they're getting some that we're not. Let's let them do the explanation here because we're just out of room. So let's let them take it over from here. All right. So let y equal r sine theta, differentiate. So y is r sine theta, which is that, which is, man, did they do this a weird way. Oh my goodness, Terrell decided to show up today. That's good to see. All right. Does anyone else come in since I called roll? Okay. Now, again, I'm asking all of you before anyone leaves, remind me to go over what the end of the term's going to be. Because otherwise I'm going to say it over and over every time someone else comes in.
Can you go over it before the break?
Okay, because you're going to have to leave then. How close are we to break time? Huh?
10 minutes.
10 minutes, okay. So just remind me, say, look, can we have a break and let's go over this then. Okay, let's see how this compares to what we did. Because I swear I don't think I would have taken the derivative quite the same way they did. They did 2 times the first time derivative of the second plus the second time derivative of the first, which is fine. And that would be that, which is exactly what we got. Then we did that, and then we did that. So we got the same place. Not sure I would have done it their way, but it's fine. And they did that as we did. So that's where cosine theta is equal to -1/2 and where cosine theta is equal to 1. And that's where theta equal. Now I guess I messed up somewhere here. When we went back and did ours, I guess we only came up with one value. Did we do 2/3 pi? Yeah, we could have gone because it was about, that's right. I was thinking the last problem where we went to pi, this one's going to 2 pi. So there were 2 places. Sorry, my bad. I was thinking we were only going to pi. At 2/3 pi, but then again at 4/3 pi. Okay, cosine is negative in the second and third quadrant. Okay, so that's, we missed that. Sorry about that. And theta equals 0, so that's fine. Then, doing the other way, we did x equal r sine theta, which gave us that, which they multiplied first, thank you very much, and then took a derivative. And that's what we got there, factored out at 2 sine theta. So dx d theta is equal to 0. So, and where it's cosine, sines equals 0 and cosines equal to 1/2. And again, because I didn't go to pi, I went only to pi, it's at pi thirds, and then cosine is 1/2 at 5/3 pi, because it's first and fourth quadrant. So that's why I missed that. Okay, sorry about that. I was just stopping at pi. So the zeros we have to throw out. The pi's were okay. Yeah. All right. So horizontal tangents here and here, and what you do is go back to your function. And they didn't have it written down here. And what was it? R is equal to, no. Yeah, R is equal to 2 times 1 minus cosine theta. Okay. And we had these various values for theta. Okay, 2/3 pi. Plug that in here. And what's cosine of 2/3 pi? Remind me? 1/2. It's negative 1/2, isn't it? Yeah. Okay. So negative 1/2. And 1 minus negative 1/2 is 3/2. Multiply by 2 and you get 3. So that's where the 3 comes from. Do the same thing here. Cosine of 4/3 pi is again negative 1/2. So that comes out the same. 3/4 pi. Okay. Do the same thing here where theta equal pi thirds. That's cosine theta is theta equal pi thirds. Cosine theta is, there's your 1/2. 1 minus 1/2 is 1/2 times 2 is 1, so that's where the 1 comes from there. 5/3 pi, same thing, that's going to be a 1/2. That's going to give you a 1. But then that pi that we had, cosine of pi is say again? Cosine starts at 1, down to 0, negative 1. So 1 minus 1 is 2, 2 times 2 is 4. That's what it is. Okay, so now we've got our points. Okay? Horizontal tangents, here and here. Vertical tangents, here, here, and here. That looks like one vertical tangent. It sort of is, but it's at 2 points. Okay, and there. And that's exactly it. And does that sort of look like something to you, Valentine's Day? A heart. So they call it a cardioid. Never, I don't know if that's what they call it, but cardiac arrest, I don't know. But it's a cardioid. Okay. So, sorry about missing one of those. Now, and notice that theta equals 0. That was one we got, right? At theta equals 0, we're here. Now that almost looks like a horizontal tangent line, doesn't it? And sure enough, we said we should have one there. But because the vertical tangent line indicated we'd have that, you can't have both. This one just happens to be. Sure enough, looks like a horizontal tangent line. Maybe it starts off at enough of an angle it's not one, but you just can't tell. Okay. So anyway, that's your cardioid. Okay. And here we have Justin. Okay. All right. We'll give a few more. When do you need to go?
Can we go ahead and do the break?
Huh?
Can we go ahead and do the break?
Can we do what?
Yeah, go ahead.
Go on and start the break?
Yeah,
do the break now?
Yeah.
Okay. So since we're going to do a break, let me go over the end of the term issues here. Okay. We're in chapter 10, 10.4. This is the last section we're going to do. In fact, we're almost through with it. So we're going to do 10.4. We're not going any further in 10. We're going to skip on to 11, and we're going to do as much of 11 as we can before the end of the term. We have class today, Wednesday, and Monday. Remember, the term goes through Monday, which means your research papers are due in this week, please, but the very latest Monday, I'll still give you full credit on Monday. After Monday, you start losing points, okay? So get your research paper in this week, preferably Monday at the very latest, otherwise you start losing points, okay? Also on Monday, I will give you your final exam. Now, unfortunately, you don't have a lot of time to do it, okay? So please focus and get it done. You can turn it in anytime Tuesday, anytime Wednesday, or anytime Thursday. Now, I can't recall if they said if the college will be open on Friday or not. The months of June and July, we had 4-day work weeks, the college was closed. Friday of next week is going to be the 3rd of August. I don't know if the college is going to be open or not. If it is, you can bring it to campus and slide it under my door. Trouble is, I'm not going to be here Friday. I've got a treatment on Friday. It's been scheduled forever, and it has to be every 8 weeks, so this is when it turns out being. So I can't be here on Friday at all. I have to be there for labs at 7. Treatment starts at 8, and it goes all day. So there's no way I'll be here at all. If the college is open on Friday, and you bring it in on Friday, you can slide it under my door. I'll pick it up Monday morning, grade it first thing, because grades have to be in by noon on Monday. No way, they don't handle any excuses. So if I don't have your grade done by noon on Monday, you're getting an incomplete. Yes?
This Monday coming up?
No. This is the Okay, this week we have class today, Wednesday, and then next Monday we have class. I'll give you your final then, and you get it back to me, preferably Tuesday, Wednesday, or Thursday. I'll be here all 3 days, okay? Then on the following Monday, that Friday of that week, if the college is open, you can slide it under my door. I just don't know if the building's going to be open or not, okay? You'll just have to see, yes.
Is the final, do you have it already made?
Do I have it made out? Is that what you're saying? No, I haven't, because I don't know. I can't estimate how far we're going to get.
Yeah.
So I'm going to try to wait until Wednesday and guess how far we're going to go on Monday, and I'll make out the final Wednesday afternoon. Okay. So, because this is the first time I've taught from this text, and I just don't know how.
Is there any way where you can email us?
Say again?
Email us the final that we printed off. Could that be
Any way you can do what?
You email us the final.
Oh, email you the final?
Yeah.
Yeah, I can. Do some of you want that to be done?
Yeah.
Just you alone or any others? Okay. You mean as soon as I make it out on Wednesday, get it to you?
Yeah.
Okay.
I'll give you my email.
Okay, well, what I might do to give it to everybody, I'll have it scanned and I'll put it on Blackboard. And that way everybody will be on the same level playing field. Okay? Because I make out the things, I do my test in WordPerfect because their equation editor is so much superior to Word. It's no comparison. So I do the test in WordPerfect, but I bet none of you have WordPerfect. And if you don't, then you wouldn't be able to read them. So, and I could convert it to Word, but Word never converts back. Well, it's just, Word is awkward. So I'll have it scanned and put the scanned copy on Blackboard. Okay? I don't know what time of day it'll be on Wednesday, hopefully before 6, but if not, I'll stay and finish it, get it out there. So you'll have it then Wednesday. You get a weekend to work on it too. All right, that also means all your tests. And let's just go over that for a moment. Test 1, I still am missing one. Well, a few have come in that I don't have graded. And so about half of them have been graded, okay? They may not all be on Blackboard yet, but they are. Test 2, have I gotten any of those in yet? Yes, a few of them came in today. So I need all of those in by Monday, Okay, your research paper in by Monday, both of your tests in by Monday. Okay, and then I'll be giving you your the last test, and I'll try to have it emailed to you by Wednesday evening. Okay, now I'll return to you everything I've got. I can't return your research papers to you, but I'll return to you your first test on Monday also. So if any of you, I'll get those to you the first thing. That's why I have to have both tests in by the beginning of class on Monday. So get them in this week, if possible, first and second test. All right, let me give you when I'll be where, okay? This week and next week. This week is normal, okay? Here all day today until 6 and Wednesday until 6. That's nothing new. Tuesday and Thursday, nothing new. I'm here from 7:45 in the morning or earlier until 3:30. Then I go to Birmingham campus. I'm there 4 to 6. Birmingham East campus. That's Tuesday and Thursday. So finals week, I have class on Monday just like normal. Tuesday, I'm here generally in my office from 7:45 in the morning until noon. At noon, I'm giving an exam here in this classroom, basically about noon till 2. It may be a little shorter, a little longer, sometimes about like that. Then, that's Tuesday. Then I'm back in the office from about 2 until 3:30. 3:30, I go to Birmingham. I'll be there 4 to 6. Okay, so if that's more convenient to you to turn something in, I'll be there 4 to 6 on Tuesday and Thursday of finals week, of next week, not this week. Well, I'm there this week, but I'm not teaching. I'm teaching this week. Next week I won't be, so you can bring it by any time. Now, where am I there? On the Birmingham East Campus is the Ethel Hall Health Professions Building, room 103. Ethel Hall Health Professions Building, room 103. It's Tuesday and Thursday afternoon of next week from about 4 till 6. Okay? I'll be there. Won't be in class, so you can bring anything by then. And then Friday of the following week, of next week, not this week, Friday of this week, school's closed, nobody's anywhere. But Friday of next week, I don't know. I don't know when we'll hear. Maybe I've already heard, just haven't seen the email. But anyway, you can check maybe at the front desk or someone and see if this college is open on Friday or not. I can't remember what they said. It seemed like they did some manipulating with it, and I can't remember which way they went. So anyway. Any questions then about wrapping up the term? Yes?
I looked at that Blackboard. Where's the instructions for the essay?
Okay. Say something else.
I was looking at Blackboard for the instructions for the essay. I couldn't find it.
Okay. Did you look under, on the home page of Blackboard, there's a whole string of tabs there, and one of them says class handouts and more, or some silly thing like that. Did you look at that one?
I guess I'll check again.
Okay. But that's where it is, and that's where all the YouTube videos are, that's where the PowerPoints are, that's where everything is. And that's where the instructions for the paper.
Yes.
And you can also go to the first YouTube video that we did in the class, and I go over the paper, so you can hear everything about it if you listen to that.
Yes.
Okay. All right. Is it break time? All right. So we'll start next time, when we get back from break on the next slide. Oh. Let's finish example 6 just real quickly. Notice both derivatives, dy dx, d theta and dx d theta are 0 when theta equals 0. Using the information alone, you do not know whether the graph is horizontal or vertical tangent line at the pole. From the figure, however, you see that the graph has a cusp at the pole, but it still doesn't tell you what the derivative is there. Well, what? Yeah. Okay. Okay, this is where we'll pick up when we come back. Okay, so let's have our break. He has an orientation at UAB that he has to be at, so he couldn't state. And I needed to find out some information from them. Okay, now, where we left off was the middle of page 724, or just below the middle. Theorem 1011, let's go back and just see Theorem 1011. Well, maybe it was on that page. Ah, there it is, 1011, there it is. The slope in polar form, this is that thing, what we've been doing. Okay, so this, it says, has some goodness gracious, this is a lot of slides. All right, here we go. This has an important consequence. If the graph of r is equal to alpha theta passes through the pole when theta is equal to alpha and L prime of alpha is not equal to 0, okay? So if the graph passes through the pole, that's the origin, okay? When theta is equal to alpha and L prime of alpha is not 0 then the formula for dy dx simplifies to be this, okay? And this is what I was looking for at the very beginning. That I think I would have started here, but they started here. Dy dx, if this thing is not 0, and sine, this is using that theorem, 1011, sorry, and plus f theta cosine, f prime theta cosine, as long as this is not 0, okay, then, but f is 0, okay, I mean, f of alpha is 0, because when theta is equal to alpha, it passes through the poles, so meaning you're at 0. So your f prime sine alpha over f prime cosine alpha is f prime of that is not 0. These cancel out, and you're left with tangent alpha. Sine alpha over cosine alpha is tangent alpha. So the line theta equal alpha is tangent to the graph at the pole. Okay, so it's 0 theta. 0 alpha. I'm saying theta. That is your, also you have a tangent line there. Now, so theorem 1012, tangent lines at the pole. If alpha theta is equal to 0, alpha prime of theta is not equal to 0, then the line theta is equal to alpha is tangent at the pole to the graph. Yeah, theta is equal to alpha, okay. Is tangent to the graph at r is equal to alpha theta. All right. Now that sort of begs the question on the last one we were doing, when you're at the pole at 0, was alpha prime of 0 equal to 0? And I just don't remember if it was or not. That would have been the horizontal tangent, things like it was. So this theorem 1012 wouldn't have fit there either. All right. Note that because the polar curve can cross the pole at more than once, it can have more than one tangent line at the pole. Let's see if that's on here too. Nope, it doesn't. Okay. But there is a little verbiage at the bottom there. Now, some special polar graphs. Okay? Several important types of graphs have equations that are simpler in polar form than in rectangular form. For example, the polar equation of a circle having a radius of a centered at the origin is simply r equal a. Period. R is equal to a. Can't get much simpler than that. Several other types of graphs that have simpler equations in polar form are shown here. This is called a limison. I don't know how you pronounce that symbol there. This is a limison with an inner loop, a cardioid, we already had that one, a dimpled limison. It doesn't make its way to the origin, it just goes in and out, okay? And a convex limison, however you say that, which bulges ever so slightly. Not a circle, but slightly convex as opposed to concave, which is like a dimple. Okay, and these are R is equal to A plus or minus B theta, B cosine theta, and R is equal to A plus or minus B sine theta. For A and B both have to be positive integers. Now, if the ratio of A to B is less than 1, you have the inner loop. Okay? So, and since A and B are both positive, that means A is less than B. Okay? If A and B is equal to 1, that's your cardioid that we saw before. Okay? This one's going in the opposite direction. Okay? The dimpled is if A over B is between 1 and 2. In other words, A is greater than B, but not twice as great as B. And then the convex limison is when A is more than twice B. Not that. Sort of a lot of blah, 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 okay? But if you need those, there they are. They're simpler. Believe me, much simpler. This would be awful to do in rectangular coordinates, that first one. I'm not even sure how you could do it there, okay? Now, here's some other special polar graphs. Your rose curves. We did the triple rose curve. Now, the end petals when n is odd, 2 end petals when n is even. That's what we sort of were seeing before. When n is odd, if you have the n theta, then you're going to have n petals if n is an odd number. If n is an even number and you have n theta, you're going to have twice n number of petals. Okay? So this would be A cosine n theta, where A is the maximum length of that radius. Okay? A is R is A cosine n theta, where and n is an even number, 4 here, that means you have 8 petals. Okay? If it was 2, you'd have 4 petals. This would be a 5 because it has 5 petals. And again, A is the maximum. Now, sort of things to note here. When n is 2n plus 1, in other words, it's 3, 7, in those, your first is on the x-axis, your A is on the x-axis, but when it's 5 and 9, they're on the y-axis, okay? Your A, your max is A. These are maxes are A2, but they're hard to see. You're obviously on A, okay? And when your n is equal to 4, your A is on either the x or the y-axis. But when n is equal to 2 or 6, for those, then you're going to be at the 45. You're not going to be at the value on the y-axis, at the max value on either axis. Okay? So, that's A cosine n theta. Or, I'm sorry. If it's cosine, your max is going to be here. If it's sine, the max is going to be on the y-axis. Okay? But if you're sine with an even, then it's not going to be there at all. Cosine will be on both of them. Sine will not be. Sorry, I said it right. Now, circles and lemniscates, okay? R is equal to A cosine theta, okay? That's going to be a circle of diameter A, okay? Whose left-hand side is at the origin. A sine theta, then A will be diameter again, but the bottom base will be the horizontal axis. And lemniscates are then with R squared is equal to A squared sine 2 theta or cosine 2 theta. Now, I don't want to project, but notice with the sine, you're just like sine here with an even n. So here your A is going to be the max at the 45s. With cosine, R squared is equal to A squared cosine squared theta, then you're going to be on the x-axis. All right, and those are just a few more of your special polar graphs. And what's the special about? Okay, now that's it for the end of the end of the section. The technology, the Rose curves described above are of the form A cosine n theta or A sine n theta, where n is a positive integer greater than or equal to 2. The graphing utility, it says use one to graph where the A for some non-integer values, and you can get some really pretty curves there. Does anyone remember the old spiral graphs or something like that? You put your pen in a thing and then roll it around, and you can come up with some figures that look like that. They're pretty impressive. All right, that finishes 10.4. Homework exercises, any of the odds, 5 through 13. All of those worked out solutions are at calcchat.com. Number 7's at CalcView as well. Do any of the odds 15 to 23, they're all at CalcChat. 17's at CalcView. Do any of the odds 25 to 33, they're all at CalcChat. 31's at CalcView. Any of the odds 35 to 43, they're all at CalcChat. 37's at CalcView. Do any of the odds 45 to 53, they're all at CalcChat. None of those are at CalcView. And 55 is a one that says verify that is a polar equation, it looks like. 57 is a sketching. 59 or 61, you can do either one of those. They're both at CalcChat. You can do 63, it's at CalcChat and CalcView. Either 65 or 67, they're both at CalcChat. 69 is at CalcChat and CalcView. 71's only at CalcChat. You can do any of the odds 73 to 79, they're all at CalcChat. 77's at CalcView. Do any of the odds 81 to 91, they're all at CalcChat. None of them at CalcView. And do either 93 or 95, they're both at CalcChat. There's exploring concepts. You can go a little deeper if you want to with 97 and or 99. They should be at CalcChat. 101 should be at CalcChat. 103 and or 105 at CalcChat. 107, any of the odds 107 to 111, they're all at CalcChat. And 113 and 115 are true false at CalcChat. They have a little special project there that's called the Cassini Oval, and named after the astronomer Giovanni Domenico Cassini. Lived back in the 16 and 1700s. I don't know if you follow space issues. European Space Agency launched a really major undertaking. It was called the Cassini-Huygens or something like that. And it went to Saturn. It took beautiful pictures and did a lot of investigation of Saturn and went on. So Cassini's name lives on, even though he was way back before space travel was even anticipated. but he was an astronomer, and they named the probe after him. Wish we had time for 10.5, 10.6. And by the way, you can look at any of these things. For instance, in 10.6, there's Johannes Kepler. He came up with the Kepler's laws of planetary motion. So potential paper topics all over the place here. It goes through 10.6. So let's move on to, well, evidently it didn't take, or it hit twice or something. So everything I just said is on there. Sorry, folks, if you missed that. You know about what happens at the end. Read that last part from where we left off in class before. We took a break. I put it on pause. I came back. When I hit it to take it off pause, it must have double-clicked and put it right back on pause. I didn't realize it. Okay. Sorry about that. Let's move on to 11. Okay. I don't know why that keeps popping up, except that it closed out everything. So I've got to go back to that. I guess something happened to the computer because I didn't close out everything, but it closed itself out. So maybe it wasn't me. Maybe something else occurred. Let's go to chapter 11. And we will end, we'll get as far as we can in 11. I'm certain we won't get to 11.6 because 11.6 is where Cal 3 begins. So I don't think we'll get anywhere close to that, but let's get as far as we can. All right. Now, let's get the slideshow set up from current slide. And did I just see that right? Yeah. Okay. We go until 1:40, don't we? We sure took that break a little early today, didn't we? We have more time left than we had before the break, so, or approximately. So let's go from here. Vectors in geometry and the geometry of space. Vectors in the plane. Now, any of you had physics already? No. Okay. Well, you have, right? Okay. This will be old hat to you, right? At least the first part here. Objectives here is to write the component form of a vector. Some pretty easy stuff here, okay? We'll perform vector operations and interpret results geometrically. A little awkward, but doable. And we'll write a vector as a linear combination of standard unit vectors. That'll be very familiar to anyone who's had physics before. So we start here, 11.1, components form of a vector. Okay. Many quantities in geometry and physics and engineering. Now this sounds a little bizarre. Area, you think of that just being a number, numerical value. But guess what? A surface has an orientation, therefore the area of that surface, well, I'm sorry. No, I'm sorry. Back that off. I was going to say, how are they doing this? Area, volume, temperature, mass, time, those are just, like I said before, you think of them as being just numbers. Single, real number, scaled to approximately units, and we call them scalar quantities. Scalar quantities. Much of the stuff in physics, geometry certainly, but much in physics as well, and specifically mass, time, temperature, and then things like area and volume are just scalar quantities. But other quantities, such as velocity, acceleration, force, momentum, and other things like this involve both magnitude and direction, cannot be characterized completely by a single real number. You have to have some orientation associated with it. Now, what I was starting to say about area, I was surprised they were mentioning now, but when you're dealing with three surfaces, usually you have a normal vector which does have an orientation. And I thought that must be why they're saying this, but that wasn't what they were intending. Area itself does not have orientation. Okay, now let's talk about what a vector is. A directed line segment. The directed part is the orientation. The line segment indicates the magnitude. Okay? A line goes forever in both directions. A ray starts at one end and goes forever in one direction. A line segment is terminal at one and terminal at the other. So it has a fixed length. That length is its magnitude. We'll talk about that later. Directed line segment, its direction also is important. So for a directed line segment, we have several ways we represent it. One way is draw it, an initial point P, terminal point Q. Initial, meaning that's where you start drawing. Terminal, meaning that's the direction you go, and stop at that point. Terminate, stop. So whenever you see a representation like this, PQ, AB, whatever, the one that's listed first is the initial point, the second is the terminal point. A single dot here, an arrow at the terminal point. Directed line segment. The directed line segment PQ has an initial point and terminal point. We got it. P is initial, always Q is the. The length or magnitude is denoted by this nomenclature. By the way, when they're saying that directed line segment PQ, notice they write it with a little arrow on top. That means it's a vector. PQ by itself would mean just a line, a line segment. With an arrow on top is a directed line segment, meaning a vector. So, if you're talking about the magnitude or the length of that line, it's sort of like absolute value bars. It's just a double absolute value bars. And there's a lot of similarity there. The magnitude of the vector can never be negative. Ever. Okay? So in that way, it's sort of like an absolute value. Okay? Directed line segments that have the same magnitude or length and exactly the same orientation or direction, those are called equivalent, and later we'll call them equal vectors. So if this vector here has a fixed magnitude at a fixed angle, that's a fixed magnitude, that's a fixed angle, same length, same directions, no matter where they are on the board, or even out here in space. Okay, well, I guess we're staying in a plane right now. But if it's same magnitude, same direction, those are equal or equivalent vectors. Okay? So the set of all directed line segments that are equivalent to a given directed line segment PQ is called a vector in the plane. So we are staying in the plane, we're not getting out into space somewhere. And is denoted by the vector V is equal to PQ. Now, notice here in the text, they write the generic form of a vector in a plane, V, and they bold the V. When I write it, I can't write in bold. So I put V with an arrow over it, just like I do PQ with an arrow over it. Okay? But the book, bold means vector. So in typeset material, the vectors are usually denoted in lowercase, bold-faced letters, such as U, V, W. Those are the favorites. Okay? When written by hand, however, the vectors are often denoted by letters with arrows over them, like U, V, W. That's how I write them. Okay, and that's what you'll see, but in the text there'll be bold-faced U, V, and W. Make sense? Be sure that you understand a vector represents a set of directed line segments, each having the same length and same direction. That vector represents any of those. In practice, however, it's common not to distinguish between a vector and one of its representatives. We just call it vector V or whatever, just any one of them. Okay? So here's example 1. Let V be represented by the directed line segment from 0, 0 to 3, 2. Okay? We'll let another vector U be represented by the directed line segment from 1, 2 to 4, 4. And then we're going to say determine whether they're equivalent. Now, I don't draw graphs well, so get over it if you get bummed out of place about my, see, it seems like everything here is in the first quadrant, so I probably should have just made a single quadrant line here. Okay, so let's tick off a few points. Here, of course, is 0, 0. We'll do 1, 2, 3, 4, 5, 6, 7, 8. We won't need that many. 1, 2, 3, 4. Okay. So here's 0, 0, and here's 3, 2. You know how to do Cartesian coordinates. There is the vector V. I write it with an arrow over it because I can't write bold. And then we have vector 1, 2. Its initial point is there. And 4, 4. 2, 3, 4. And 4 is somewhere right about here. So there is vector U. Now, how can we show those are equivalent? Okay? Well, two things must be true for a vector to be equivalent. Magnitude has to be the same and direction has to be the same. Now, they haven't told us yet how to do either one of these, but you sort of know, I think. This is the point 3, 2, and this is the point 0, 0. This is the point 1, 2, and this is the point 4, 4. How do you do magnitude? Remember, that's the same as length. Do you remember the length or the distance formula? Same as distance. The magnitude of V would be the square root of, and you can pick either one to be initial and final, it doesn't really matter. I'll give you the formula. x2 minus x1 squared plus y2 minus y1 squared. Okay? It doesn't matter which one you put first or second because you're squaring it, so it doesn't matter. So this will be the square root of 3 minus 0 squared plus 2 minus 0 squared, which would be the square root of 9 plus 4 equals the square root of 13. All right, that length we know, magnitude we know. Do the same thing here. The magnitude of U would be the square root of 4 minus 1 squared plus 4 minus 2 squared. And just a little bit of attention to this would be 3 squared plus 2 squared. It's exactly what we got down below. That's equal to the square root of 13, too. Does that mean these two are equivalent or equal vectors? No, it means the magnitudes are the same. What also must be the same? The direction. Now, how is a good way to talk about the direction of the vector? Well, one way that you've done before is slope. And what's slope? Rise over run. So let's see what the slope of this vector is. The slope, I'm actually going to, okay, the slope of V, this is my nomenclature here, rise over run would be 2 over 3. The slope of U would be the difference here. Rise would be 4 minus 2 over 4 minus 1, which would be 2 over 3. Yes, same slope, same magnitude, identical or equivalent vectors. So yes, you were right, they are equivalent. But you have to show both of those to be the case. Now, actually a little more precise than slope would be the angle at which they are from the horizontal. And that angle would be, what is the ratio of rise over run, or y over x, relative to this angle here, or this angle here with the horizontal. Rise over run. Opposite over adjacent is tangent. So tangent alpha, that's actually the better way to go, which is exactly that. It's the rise over run. Okay? So, they actually, without having told us this, they used the distance formula just like we did, and then they did the slope just like we did. And since they have identical magnitudes and identical slopes, they have to be equivalent vectors. Okay, so let's clear this and see how they did it, which I think is identically the way we did it. P and Q, 3, 0, 0 to 3, 2, be the P, 0, 0, the initial, and 3, 2, the terminal points of V, R, 1, 2, and S, 4, 4, the initial and terminal points of U, as shown here. They sure look like they're parallel. They sure look like they're about the same distance, but you have to actually use the distance formula to show that the magnitude of the length of PQ and RS, they have the same lengths. So the magnitude of PQ is 3 minus 0 squared plus 2 minus 0 squared is square root of 13. And RS, that's PQ, RS, magnitude of that is square root of 4 minus 1 squared plus 4 minus 2 squared, which again is 3 squared plus 2 squared equals square root of 13. Both line segments have the same direction because they both are directed toward the upper right on lines having the same slope. Okay, because the slope of PQ is rise over run, 3 minus 0 over, no, 2 minus 0 over 3 minus 0, 2/3. Slope of RS is 4 minus 2 over 4 minus 1, which is also 2/3. Because they have the same length and the same directions identically, you can conclude the two vectors are equivalent. Therefore, vector V and vector U are equivalent. Later, we will actually say they're equal. Right now, they just say equivalent. The directed line segment, whose initial point is the origin, is often the most convenient representative of a set of equivalent directed line segments like this. So vector V would be the way we usually want to represent all those vectors, even R. We just translate it down. There are other times we want it off the origin, and you just translate it wherever you need to go. Now notice I said translate, meaning we can move horizontally or vertically or both. We can't do any stretching and we can't do any rotating. Either one of those, we have to just translate. Right, left, up, or down. That's the only freedom that we have of moving these things around. This representation of V is said to be in standard position. When the initial point is at the origin, terminal point, it winds up wherever it happens to be. Now, here's a little bit of nomenclature, okay? What do you call it? Convention, how we represent this. When we're talking about this point up here, Q, we give the horizontal component and we give the vertical component. Okay, since we named this vector V, the horizontal component we'll call either V sub 1 or sometimes V sub x, and the vertical component is either V sub 2 or it could be, since that's listed as the y-axis, V sub 1. Okay, so this point here in parentheses is V1, V2. In this case, it looks pretty close to 3, 2. I don't know if it's exactly that, but it's pretty close to it. V1, V2. If you're talking about the vector, however, you do not use parentheses. You use what I call angle brackets. I've never seen an actual term for it, but that's what I call an angle bracket. These are the coordinates of the point. These are the components of the vector. Now, these words sound alike, but they're different. Coordinates of a point, components of a vector. And they're written same way. Now, here is the bizarre thing. You don't have to be worried about this. I think that Justin may already be aware of it. I can't remember. Nicole, did you take linear algebra? No. In pre-calculus algebra, we use pre-calculus text by Ron Larson. Okay? In calculus, we're using his text as well. In linear algebra, we're using his text as well. Okay? And linear algebra deals pretty much with vectors as well. And when they're talking about a vector in his text, in same author, he puts parentheses around it. So looking at them, you can't tell a difference. You have to tell that by context. And I don't know why, because I teach several courses out of 5 courses out of these 2 books, 1 course out of the other one, and every time I have to remember, oh, I can't use the angle brackets because he only uses parentheses there. I don't know why. So if any of you take the course here, you'll see when we get to vectors, he uses parentheses rather than angle brackets. And I have no clue why. Never has explained it. All right. In the definition, note that the difference in the notation between the component form of a vector and the point, they've got this wrong. This should be parentheses here, not angle brackets. In the book, do they have it right? Yeah, in the book, those are parentheses. Whoever did the typesetting here got it wrong. Those are parentheses for a point, angle brackets for a vector. They said, note the difference. They didn't show them. These are parentheses for a point, angle brackets for a vector. So the definition of the component form of a vector in a plane, if V is a vector in the plane whose initial point is the origin, whose terminal point is the point, parentheses V1, V2, close, then the component form of V looks exactly the same except the angle brackets. So if it's a point, P, Q, something like that, then it's parentheses. If it's a vector, V, boldface, whatever, then its components are angle brackets V1, V2. Coordinates V1 and V2 are called components of, I hate they say that. They are the coordinates V1 and V2, but when they're in angle brackets, they're called the components of V1, of V, okay? If both the initial point and the terminal point lie at the origin, then V is called the zero vector and denoted by bold 0, 0, 0 in angle bracket, because this is a vector there. Now, can one think of any potential problems with the zero vector? Second? Okay, very good. Nailed it right there. Actually, there's 2 things wrong with it. What's its magnitude? 0. Okay, it has no magnitude, and what's even worse, what angle is it? A zero vector has no length, so what direction is it pointing? It has no direction, okay? So a couple of issues with it, but we still have to have it there for other reasons, okay? This definition up here, implies that any 2 vectors, U, which is U1, U2, and V, which is V1, V2, are equal. Now we're not saying equivalent, are equal if and only if U1 is identically equal to V1 and U2 is identically equal to V2. Now, when I say identically equal, does that mean they have to look just alike? If U1 was 2 and V1 was 4/2, they're the same. They're equal to each other. They may not look the same, but they are. 2 is 4/2 or 6/3 or whatever. So if they are equal, whether they're in the same form or not, 2 square root of 4, same thing, okay? Doesn't matter, okay? But if those 2 are equal, the first components are the same, second components are identically the same, then these are equal vectors. All right, the procedures listed below can be used to convert directed line segments to component form or vice versa. Okay, so here we have a point P, and most of the time points are given capital letters but not bold. Okay, and usually when you're given a point, quite often they'll put in parentheses components, the coordinates, I said it wrong, coordinates of that point, P1 and P2. And here's point Q, which is, its coordinates are Q1 and Q2. So they're the initial and terminal points of the directed line segment. Then the component form of that vector V, represented by PQ, where P is initial, Q is terminal. That's what that means. Initial is the first letter, terminal is the second letter. Okay? V1, V2 would then be simply Q1 minus P1 is the first component, Q2 minus P2 is the second. Moreover, from the distance formula, you can see that the length of the magnitude of V would be the difference in this squared plus the difference in that squared. Q1 minus P1 squared plus Q2 minus P2 squared. And the square root of V1 squared plus V2 squared, where whatever, since this is V1 and that's V2, it's just V1 squared plus V2 squared. Square root of that. That's the magnitude of V. So there's lots of equivalent ways of writing equivalent things. Okay. All right. Now, if V is V1 and V2, vector form, angle brackets, components, okay, then V can be represented by the directed line segment in standard position from P00 to Q, V1 and V2. If you write, okay, that V could be from any 2 points anywhere, but if you put it in standard position, you know its coordinate is component. Right? The coordinates of the point, terminal point, will be exactly the components of the vector form. Okay? So Q will be the point, parentheses V1, V2. The length of V is called, here's another name for it. We call it length, we call it magnitude. Here's another one, the norm of V. Why do we have to have so many different words? We need the same thing. Well, people in different fields dealt with them and then found out they were all the same thing. So the norm of V, so the magnitude or norm, length of V, okay, I'm sorry. If the length of V is 1, then V is called a unit vector. In other words, if its magnitude or its length or norm is exactly, precisely 1, no matter where it's oriented, but it's exactly 1 unit, then V is called a unit vector. Okay? Uno meaning 1. Moreover, if the magnitude of V is 0, there's no way that has to be V has to be the 0 vector. Notice the number 0 is written without bold. The 0 vector is written bold. So therefore, when I write the 0 vector, I put the little arrow over it. So you know I'm talking about a vector, not the number 0. Okay. It seems like to me they skipped example 2, didn't they? Yeah. So let's go back and see if we can find a place to do example 2. That looks like maybe the best place for it. Find the component form and the length of the vector V that has initial point P is 3, -7, and Q, terminal point, -2, 5. Oops, there's terminal point Q. So we want the component form of V. Component form will live inside angle brackets. That makes it a vector that's component form. What would be your first component? between the vector going from P 3, -7 to Q, -2, 5. What will be its component form? A little louder. You said 3 and -2. Is that what you said? I couldn't hear. No, you may have said it right. I'm just asking. What did you say? Okay. Now, there's an operation that has to be there. It's not just a number. Yeah. What operation? And in which order? Second? It has to be terminal minus initial. Terminal minus initial. So it would be -2, the terminal x value, minus the initial x value, 3. And then what would be the second component? Five minus a -7. Okay, so let's clean that up a little bit. What will that be? -5, 12. Perfect. There is your vector in component form, -5, 12. Okay? Now, it said, and the length of the vector. So the length of that vector, magnitude of the vector v, would be what? How do we define that? Square root of, second? Okay, you can do it that way. The x2 would be -2 minus 3 squared plus 5 minus a -7 squared. But if you notice that, we could have just gone straight to our component form. That would have been -5 squared plus 12 squared, because we already had done that. So we could have just gone straight to this. And what would that be? The square root of, what's -5 squared? 25, positive, remember, plus 144. And what's the sum of those two? 169. And what's the square root of 169? 13. The magnitude is lucky 13. Okay? Makes sense? And actually, since you had already done this, you could have written the magnitude as just v sub 1 squared plus v sub 2 squared. So, good deal. That was example 2. Now we're ready for vector operations. All right, vector operations. Here's the definitions of vector addition and scalar multiplication. So let's let U be these components, U1, U2, is normal. Vector components. VB, V1, and V2, that's normal. They're both vectors. Let C be a scalar. Any number in the world, any real number, including 0, but most of the time not, any real number. Positive, negative, fraction, decimal, rational, irrational, it doesn't matter. Real number. Does not have any complex scalars yet. Okay, just real number. So, first, the vector sum of U and V is then the vector U plus the vector V. That's how we represent it. How do we actually express it? We add the first component to first component, and that makes the first component of the sum vector, comma, second component plus second component, and that makes the second component. It's that simple. Now you can do it other ways. The component notation is the easiest, best, most precise way to do a vector sum. And it's just so straightforward. Now, we have another operation we call the scalar multiple of some vector U. So we're supposed to take that scalar number, just a number, and multiply it by this vector U. So C times U would be C times angle bracket U1, U2, which then is just C times U1, comma, C times U2. You just distribute the C, the constant, across the angle bracket just like you would in parentheses, and that's it. Now notice what you've done. You've scaled either up or down the X and the Y component, so you wind up with a vector that is the same direction, but scaled differently. Either longer if C is greater than 1, shorter if it's less than 1, negative if, between 0 and 1, and negative if it's negative. So, and here we get to that. The negative of vector V is when you scale it with a negative 1. So you multiply negative 1 times V, which is negative V1, comma, negative V2. So where the V may have been going this way, negative V is going that way. Both things have changed directions. Okay? Exactly opposite. 180 out. Okay? Now, what is the difference? Here we have the sum of two vectors. The difference of two vectors would be U minus V, which is the same as U, the first vector, plus the opposite of V, the second vector. Okay? And that would then be U minus V. U1 minus V1. U1 minus V1, comma, U2 minus V2. Okay? So it's just like you would expect. The easiest way to subtract vectors or scale vectors or add vectors is to do it in component form. And it's just so straightforward. Exactly like you would expect. Later they're going to show you ways to do it graphically, and so easy to make mistakes with that. This way is so incredibly straightforward and correct. Okay. Now, geometrically, the scalar multiple of a vector V and the scalar C is that the scalar multiple of a vector V and a scalar C is the vector that is the magnitude of C times as long as V shown in this figure. So if this is your V, then 1/2 of V would be in exactly the same direction, but half the magnitude. 2V would be exactly in the same direction, but double the magnitude. Minus V would be the same magnitude, but in exactly the opposite direction. And minus 3/2 V would be in the opposite direction and 1.5 times the magnitude. Okay? So that's what it means to deal with a scalar. And these are very simple. 1, 1/2, 2, minus 1, and minus 3/2. You could have all sorts of multiples or things there. Every vector would be, they would all be parallel to each other. Just one end might be in the opposite direction of the other, and the magnitudes would change. If C is positive, then CV has the same direction as V. If C is negative, then CV has the opposite direction as we see. They're all parallel to one another. Make sense? Okay. Now, the sum of two vectors can be represented geometrically by positioning the vectors without changing their magnitudes or directions. They have to be the same vectors, so that the initial point of one coincides with the terminal point of the other, as shown here. If this is your vector U, and there's your vector V, obviously, now I don't know, they may have close to the same magnitude, but they definitely have different directions. If you're going to add U to V, I usually start with U, okay, draw it, then take V and put the initial point of V on top of the terminal point of U, move it up here without changing its orientation, its direction at all, and then from the initial point of U to the terminal point of V, that will be the sum vector U plus V. Now this is called graphical addition, geometrical addition. Sometimes it's called the parallelogram method, because if you write the opposite of them, V plus U, you get the lower part of the parallelogram. This would be a diagonal across the parallelogram. But that's exactly what you do. And, as I just said, if you had started with u and then took v without changing its magnitude or direction, then the magnitude, the u plus v vector, would be identically the same. Not in the same location, but same magnitude, same direction, so the same vectors, and therefore vector addition is commutative. Doesn't matter which order you add, u plus v or v plus u, they're the same. They wrote it as if it's still u plus v, and it is, but that's because they are the same. Okay? So that's one vector operation with a geometric scaling, okay, or geometric representation, which really, this is a geometric representation too of your scalar multiplication. Now, and the vector u plus v is called the resultant vector, okay? Now, we use that in several contexts. Have you done your E&M physics too? Okay. When you get into that, you'll probably run into vectors that represent resistances, capacitances, and inductances, and they will have vectors with different orientation. The resultant vector will be the overall component vector that you're dealing with. Your voltage and current depend on those, how they're staged together. So the vector is the resultant vector is the diagonal of a parallelogram. That's why it says sometimes called a parallelogram method. Having u and v as the adjacent sides, and it doesn't matter which side it's with. Figure 1118, that's the 11.8, that's this one, shows that the equivalence of the geometric and algebraic definitions of vector addition and scalar multiplication, and presents at the far right the geometric representation or interpretation of u minus v, which I do not find that useful, but you can do it. Okay, so it's vector addition. If this is your vector u, now they put them now down in standard position. They move vector v back here and vector u down here, so they're standard position. Fine, it's perfectly fine. Okay, so this, the terminal point is now v1, v2, just like the components of v was angle bracket v1, v2, and the components of u are u1, v2, just like the coordinates of the point up here is u1, u2, just like the components of the vector in angle brackets for u1, u2. So let's take a look at this. This is your v1. This is your v2. Here's your u1. They don't show it well here. Right here they show it, which is the same as here. And there's your u2, which they show right here. And if you take a look at that, v1 plus u1 gives you your component here, and v2 plus u2, that gives you a component here. And that is exactly the same, and you see the vector addition, the component addition, the parallelogram position, everything is the same. Scalar multiplication, same type of deal. Here's your vector u, which is u1, v1. No, u1, u2. And then when you scale this up with a number, this happens to be greater than 1. In fact, it looks to be between 1 and 2, approximately. Actually, between 2 and 3, maybe. Okay. You're scaling up u by k and v by k, and that gives you ku1 times k, or common ku2. Now, they're showing this as coordinates of points. You could also show it as components of vectors. Now, here's your vector subtraction. Okay? If you start with u and are going to subtract from it v, then you do u plus a negative v. Well, negative v is going to be in the opposite direction, but then put its initial point, this one, at the terminal point of u, and then draw it in the opposite direction, negative V, and this will be your resultant there, vector subtraction. The better way in my mind than to try to do this kind of thing is to do U1 minus V1, comma, U2 minus V2. It's so straightforward. It exactly looks like what you should get. You'll get the right answer, and you don't have to worry about, wait, no, what coordinate do I put where? It just makes more sense. Okay? And I don't know why they did this, but to me, this is U minus V, but that is too, because they're parallel to each other, same magnitude, same direction. But I would have labeled this as U minus V, and maybe this is U plus negative V, I don't know. They are the same. Okay. Any questions on that? All right. Do we have time for example 3? What do you think? Yeah? Okay, let's do it quickly. Here is V is negative 2, 5, and W is 3, 4. Find each of these vectors. What is 1/2 V? What would that be? I drew it as if we're going to write it in component form. I think that's the easiest to do. What would be the component of the first component of this new vector, 1/2 V? Say again? Okay, no, you're not adding, you're multiplying. 1/2 of negative 2 is negative 1. 1/2 of 5 is 5/2. Okay, 2.5, whatever you want to call it. Okay, W minus V would basically be, write down W, 3, 4 minus negative 2, 5, negative 2, 5, I can't write. Okay, and these are angle brackets. Sometimes I get in a hurry writing and they don't look very angled, but that is. And what would this be? 5, because 3 minus a minus 2 would be 3 plus 2 is 5, and say again? Negative 1. Perfect, perfect, perfect. 5, negative 1. I left an awful lot of space there. Okay, how about V plus 2W? That would be negative 2, 5. That's your V, plus 2 times 3, 4. If you write it in component forms, it's really pretty easy to do. What would that be? 4. Negative 2 plus 6 is 4. Say again? I can't hear you. Okay, 5. Yeah, 5 plus 8 is... Say again? 13. Okay. You're trying to throw me off, I can tell. Okay. All right. Let's see how, that's how we did it. Let's see how they do it. If they, okay, the A is just taking half of each of those, and you get negative 1, 5/2, just like we got. Or subtracting those two, rather than trying to draw graphs and stuff like this, just subtract. W1 minus V1, comma, W2 minus V2, that would be 3 minus a minus 2, comma, 4 minus 5, 5, negative 1. Just like you said. And the C, using 2W to be 6, 8, which I wouldn't necessarily have done it that way. V plus 2W would be negative 2, 5, plus 6, 8. We just multiplied it out as we went. That's fine. This is fine too. That would be negative 2 plus 6 which is 4, and 5 plus 8 is 13, which we finally got to. Make sense? All right, we'll begin next time because I don't think we have time for it, right? We'll begin next time on the properties of vector operations. Okay? I think we got, and by the way, we skipped right over William Rowan Hamilton, who did a lot of the early work with vectors, lived way back, and later Maxwell, who lived part of the same time, restructured Hamilton's quaternions, he called it, for what we use as vectors today. So he was sort of the founder of vectors. And then there's a very interesting little blurb there about Emmy Noether. And just to show how impressive she was as a mathematician, when Albert Einstein had math questions, he usually went to Emmy Noether. Okay? He didn't really care for math as much as he did physics, so when he sort of got bogged down with math, he'd go to Emmy Noether. They had some things in common. They were both German Jews who had to flee Hitler in World War II. Both came to the U.S. The sad thing about Emmy Noether is she had a routine operation, gallbladder or something like that. Something went terribly wrong on the operating table and she died. And she could have, who knows what all she would have done. Anyway, 2 more potential paper topics, or several if you wanted to get involved with it. Let's look at our homework exercises here. I think you can do number 3. I think you can do, and it's at calcchat.com. 5 or 7 are both at CalcChat. 5's at CalcView. 9 through, any of the odds 9 through 15, they're all at CalcChat. 11's at CalcView. A little bit different kind of a problem, number 17, is a CalcChat, if you can't figure it out, but I think you can. Any of the odds 19 to 23, they're all at CalcChat. 21's at CalcView. You can do 25. I think that's pretty easy. It's a CalcChat if you need it. 27 you can do also. It's a CalcChat and CalcView. And then somewhere there you can stop, and I think that's as far as you need to go. And we'll pick up the rest of those next time. Good deal. Any questions? Good deal. Again, folks, I'll apologize ahead of time. I'm behind in grading. I'll try to get caught up beginning Wednesday afternoon. I already have had a student saying he's coming by for tutoring then, so that'll shoot me further behind, but I'll try to get caught up as soon as possible.
You said for the final.
What's that?
You said for the final. You have to have it this same week.
Okay, I can't hear you. Sorry.
For the finals, like.
Oh, final?
Yeah, do we have to have it in that same week?
Do you have to what?
Like have it in back to you this same week?
Yeah, well, if you don't, you're going to get an incomplete. Okay? But as soon as you get it back to me, I'll change the incomplete to a grade. But yeah, and like I told the others, he asked if I could do it. As soon as I get it made out, then I'll try to get it scanned and put on Blackboard, and that'll probably be Wednesday of next week, and then that'll give you the weekend extra to work on it. And it'll be due anytime the next week. Tuesday, Wednesday. Technically, it's due on Wednesday, but if you want to turn it in early, you can do Tuesday, anytime Wednesday, or anytime Thursday. If the school is open, you can bring it by Friday. I won't be here because I know I've got a treatment on Friday, but I'll if the school's open, you can slide it on my door anytime Friday. And when I come in Monday morning, I'll grade it then. But you see, grades are due by noon on Monday. So at noon on Monday, if I don't have everything, it's an incomplete. Then as soon as you get it to me, I'll get it changed.